So good morning and welcome to the Communication and Signal Processing Seminar. It's a different time today because we have the speaker from Israel. And so before I hand over the reins to Laura, just wanted to thank the research areas for supporting this group for the seminar series. And Laura, please go ahead.
Great, thank you. So everyone, today we're very pleased to have Professor Yonina Eldar here to present to us on her research. Professor Eldar is a professor in the Department of Mathematics and Computer Science at the Weizmann Institute in Israel. She is an IEEE and EURASIP Fellow and has received many awards, too many for me to list here today, but they include the Signal Processing Society Technical Achievement Award and the Kiyo Tomiyasu Award, which is also for an outstanding career of technical contributions. So her work has consistently been at the cutting edge of signal processing and bringing new applied math techniques into our field. And the work you'll hear about today continues that trend. So we're very excited to hear about it and happy to have you, Yonina. So we look forward to your presentation.
Thank you so much, Laura, for that super kind introduction. So I appreciate it very much. And in general, I really appreciate the invitation. It's been a long time since we've been able to, get together and see each other. So this is not the same as being in the same room, but, as close as it gets. So thanks a lot. And I do apologize. You can hear in my voice. I have some sort of cold, not COVID. We tested already, but hopefully my voice will still come through loud enough. If it's not, let me know and I'll, try to make it a little bit louder. So great. So thanks everyone. Is it okay? It's coming through
really
okay?
Quickly. Yeah, no, it's wonderful. I also have a cold, so I totally understand. Let me say quickly that I will be monitoring the chat. So anyone who wants to ask a question, please, either interrupt Professor Eldar if it's, sort of urgent from what she's talking about, or you can write it in the chat. Yonina, you don't need to monitor that. I will, and I'll ask the question when it's appropriate.
Okay, great, thanks. And actually, I was just going to say that I really appreciate questions. So, do feel free to ask and it will make it more lively and interactive for everyone. So great. So again, thanks a lot. And what I want to talk about today are ideas that, of course, many people in the community are working on how we could acquire, communicate, process signals much more efficiently than what is being done today. And we'll start with talking about, some older elements of compressed sampling that, I'm sure many people here are very familiar with, but that will just set the stage. And then we'll move on to newer tools that integrate also deep learning methods. And in particular, we'll try to show different applications and systems that we've been working on that actually implement these ideas in practice. So, sorry. Okay, good. So, as everyone knows today, right, we have tons of data. We're generating huge amounts of data. And this always looks like a good thing, like we have a lot of data to do everything we want, but it also, of course, comes with a cost. So the power consumption of the IT industry is actually higher than some of the big countries. It takes an enormous amount of storage area. So here we see, one of the 3 million data centers worldwide that, is just storing our information. We, of course, use a lot of power to process it, to communicate it. And actually a recent study by Cisco predicted that by 2022 the internet traffic will approach a zettabyte, which is 10 to the power 21. So, these are numbers we can't even imagine. And the question is, do we really need all of this data for the types of questions that we end up asking on this type of data? So why would we think that we could get away with less data? Well, if we look at medical imaging, for example, which is one of the areas that we've been working in a lot, and I know there's a lot of people by you that have been working on it. So take, for example, an ultrasound machine. It's kind of like MIMO radar. So we have many elements, and each of these elements are acquiring analog signals. But at the end, we take all of this analog information and predict it down to a single image or a series of images that are used for diagnostic purposes. And, a similar thing happens in MRI and CT and many other modalities. So the underlying analog signals are much richer and contain much more information than we're actually using at the end to make our diagnostic decision. If we look at, smart cities, autonomous vehicles, today we're mounting these vehicles with more and more sensors. So we have radar, LiDAR, ultrasound, vision. But at the end of the day, when we need to make a decision, when the car wants to know if it should make, a right turn or not, it's not actually using all of this information all of the time. There's just no way that it could keep up with the speed of information. Of course, a very prevalent example are deep networks. So we know, of course, that we could train deep networks with thousands and thousands of examples, and it will perform quite well. But we also know that, a little child could distinguish very easily between cats and dogs by seeing 2 examples or 3 examples. So all of these are examples that show that, we kind of gone into this mode of let's collect all the data and then we'll figure out later what we're doing with it. But now that we're hitting kind of an explosion, we want to revisit that and see if we could only acquire the parts that we're actually going to need for the tasks that we're interested in. Girl in a digital world. So hopefully you can hear that. That's a cool song by Judy Gorman, who sings about being an analog girl in a digital world. And, that captures very nicely what we're talking about here today, because when we say data, obviously we mean bits, so digital data, but the underlying signals are, of course, real physical signals that have to be sampled and digitized. And of course, today, essentially all ADC converters are working at the well-known Shannon-Nyquist rate, both for analog to digital conversion, the sampling part, and of course for quantization as well. So in fact, if we take a closer look at the way acquisition systems are built today, they're built in a very modular fashion. So say we have a radar signal that we want to acquire, what we're typically going to do is first sample it. And this will be based on the Nyquist theorem or higher. We're then going to quantize the samples, and this will typically be based on the rule of thumb that, for each bit that we're going to add, we're going to get 60 B's SNR. So we're going to determine the number of bits by the required SNR. And then only after we're in the digital domain do we take into account the specific task we're interested in. So if this is radar, for example, we might be interested in computing a delayed Doppler map. And then what we're going to do is we're going to take all of these signals and beamform them. So basically align them to look in a particular direction. So, we're taking all of this information, all of these bits, but at the end, what we really want to produce is this delayed Doppler map, which is obviously much lower dimensional than the underlying continuous time signals. So the point here is that each block is optimal, but it's being optimized separately and independent of the task that we're interested in at the end. So this, of course, comes with the price, and it works because it's obeying the individual theorems. But when we start looking at large bandwidths, like in high rate communication or high resolution in radar or imaging, we'll see that this method ends up requiring very high sampling rates, very high quantization rates, which, as we said already, they're costly, they consume a lot of energy, they're difficult to process, to store and transmit, and there's other trade-offs as well, more physical trade-offs. So if we look, for example, at medical imaging, then this will translate directly into large, long scanning times, high radiation dosage, etc. So at the end of the day, this ADC, which is the front end of all of our digital devices, leads to various different bottlenecks that we want to try and overcome. So what we're going to look at in the talk today is trying to overcome these bottlenecks by looking at, joint design systems where we no longer design these blocks independently, but rather we're going to look at joint designs using both more standard tools like compressed sensing, but also more advanced tools like deep learning tools, where when we do this joint design, there's 2 particular things we're going to take into account. One is the structure, and the structure could be in the input, like we're used to from, let's say, sparse recovery, but it could also be in the system itself. And the other thing we're going to take into account is the output task. So different tasks could require different system designs that will be more efficient. And what we're going to see is that the same principles we use in order to do this joint design could also be used to get what we call model-based and interpretable data-driven methods or deep networks. So the same elements could be used in deep networks, even though that's a digital problem and not an analog problem. So some of the advantages we could get from this type. Sure, yeah.
A quick question before, just more like a philosophical question. So in some sense, you're going, from what I'm gathering, is that based on the task you're doing, you want to compress the data that you're gathering. But if you want to do 2 different tasks or 3 different tasks, maybe each wants a different form of compression. And if you're not retaining the data, then you're going to do poorly on those. That's one. And then if you say collecting data at different areas and there's something that's buried in noise, only when I combine all the data do I actually see it. That would be another place where this compression in the beginning will lose fidelity.
Yeah, those are really, really good points. So thanks for those questions. So you'll see as we go through the talk, when we talk about tasks, we actually refer to very, very global tasks. So it's not like something very specific, but it's more like the system operation. So for example, if you think of radar, right, like radars are I think never or almost never used to recover the underlying analog signals. They're used to detect targets, to track targets. So when we say tasks, it's more a system level task. Okay, so it's something that you're right that if I was looking, you could look at lower level tasks as well, and that we look at as secondary steps. But in the RF hardware, which like you're saying, I'm not going to go and change per task, we look at tasks that are very, very general for that system design. So I hope that kind of clarifies that.
Thank you. Yeah.
Okay, great. And families of tasks are also something very important, right? So we want to be general enough that we don't have to change the hardware, every time we change some low-level design, but not too specific that we're not gaining anything. And hopefully the applications will make that a little bit more clear. So some of the things I'll just skip through this quickly. So some of the advantages that we're going to show, depending on time, is that we could, of course, get very small devices. We could have joint systems, for example, joint radar and communication on the same platform, since each of them is going to be done efficiently. We could do very efficient wideband sensing, efficient radar, MIMO systems. We'll talk quite a bit about low bit quantization that stems from this. We'll say a little bit about super resolution, which is kind of the flip side of sampling. And then at the end, we'll talk a little bit about how the same ideas could be used for what we call model-based deep networks. So more specifically, we'll try to kind of break up the talk into three different parts. So one focusing on structure, which is kind of older ideas of compressed sampling with some newer applications. We'll then talk about the tasks, and we'll see the type of task we're referring to. So hopefully that will clarify that issue. And then we'll talk at the end about how we use these ideas for model-based deep learning. So let me start with older work, but that will kind of set the stage for some of the newer stuff, where we basically are looking at structure, different forms of sparsity or more generalized notions of sparsity. And this leads to what we called a while back sampling, compression and sampling, and done simultaneously. And these are all systems that we've developed based on those ideas. So, the oldest thing that we looked at almost 10 years ago already, so time flies when you're having fun, is this multiband problem where we have a signal that has several narrow bands of information, but these bands are spread over a wide frequency range. Now, of course, if we know the carriers, we could just demodulate each signal down to baseband and sample it in baseband, but we're looking at cases where we don't know where these frequencies are. And of course, any such signal you could sample at the Nyquist rate at F max, but that would be accommodating signals of this form, which have no structure. So what we want to do is capture the structure in the analog domain without discretization or anything, and then use that to reduce the rate. So this was some of the older work we looked at. More recently, we've been looking at similar problems, but in the imaging domain. So any imaging modality that's using multiple frequencies, like multispectral imaging or multispectral CT, you could treat mathematically in a similar way. Another example that also dates back quite a while ago, and the really nice work of Vetterli and his colleagues, and there have been many extensions to that, are problems that are based on streams of pulses. So, for example, in radar, you send a pulse, you get reflections of this pulse, where if you know the time of arrival, you could recover the distance to the target, and from the amplitudes, you could recover the velocity. In our group, we've been looking a lot of generalizations of this to ultrasound, which on a high level you could think of as very similar to radar. You send a pulse through an ultrasonic probe and you're basically viewing reflections of the tissue. Ultrasound is a little bit more involved, first of all, because it's near field. Second of all, because the environment is really, really noisy, much more noisy than radar. So in practice, it's more like MIMO radar. You have, at least 128 elements within the probe. You receive the signals in all of these elements, and then basically you do beamforming. It's nonlinear beamforming because it's near field, but it's the same concept of beamforming in order to get a very focused beam. but you have to do this for every point in the image. So it's a very, very costly operation. And that's one of the reasons that ultrasound machines are so big. So in this case, the problem is not only to sample at a low rate, but it's to do all of the processing at a low rate as well. And this more relates to the task, to looking at, compressing the task, which is always the same in ultrasound. So the task here is always beamforming, but it is a particular task. And what we'll see is that by doing this compressed beamforming or this compressed task, we could get a lot of different advantages. I'll talk more about the advantages we get in ultrasound later on in the talk. So we've seen two examples, one in frequency and one in time. We could look at a much more general class of functions, which are called union of subspaces. So again, those working in compressed sensing are familiar with these notions, but the idea is that you assume that your signal lies in some low dimensional subspace. You just don't know a priori which low dimensional subspace. So you have many, many options. The signal is in one of them. And what you have to do basically is detect the correct subspace and then recover within the space. And the nice theorem you could prove in the context is that, at least in terms of sampling rate, the rate that you need is the rate associated with the sum of two subspaces, independent of how many options you have. So even if you have infinitely many options, the rate is determined only by the sum of two. And that's why the rate could be much, much lower than the Nyquist rate. So this is the basic theorem that kind of paves the way to low rate sampling. In practice, over the years, we've developed what we call the sampling framework that allows you to actually achieve this minimal rate in many different applications using very convenient hardware. So here we see some of the boards and systems we've developed for different applications. They all follow the same principle. So the idea is to take the signal, to alias it. So basically what we want to do is we have all of these subspaces. We want to kind of linearly combine them, make these mixtures of these subspaces, but this is done in the analog domain. So we do that by multiplying with a periodic function. And we know that any periodic function in time is going to be a delta train in frequency. So if we take, for example, the multiband problem, after multiplying it with a periodic function, we get, shifts to the right, shifts to the left, everything gets summed up, and we end up getting kind of this mixed up aliased signal, which we then filter. So we only take one window of it. And then if we have one window, we could easily sample at a low rate. So this is what we're doing in the analog domain. We then sample at a low rate using a very simple analog to digital converter. And then after we sampled, we could use ideas of compressed sensing to locate the correct subspace and then recover within the subspace. So that's kind of the basic flow for all of these different problems. We could prove that that flow, first of all, could be implemented efficiently in hardware. Second of all, it has various different optimality properties. So it's optimal in the presence of noise, in terms of mean squared error, and in terms of capacity if we're looking at a communication problem. And as I said, we use these mixing ideas in the analog side. On the recovery side, we use compressed sensing to locate the subspace. So we could think of our underlying vector as being an indicator to the correct subspaces. So I know I'm going through this rather quickly. I'm kind of assuming that everyone has, background in these areas, but even if not, this is basically all you need to know for the rest of the talk. So more older ideas in compressed sensing, we're looking at the simple linear problem. Over the years, there's been many extensions also by people on this call here today that looked at various different extensions of compressed sensing. So a lot of work has been done in our group and others at looking at nonlinear problems. And we were motivated by different problems in optics. There's been a lot of work in the context of MRI where you have multiple images. We've looked at sparsity with tracking, for example, for ultrasound. And more recently, there's been a lot of work where instead of using standard compressed sensing methods like OMP and methods like that, there's been a lot of work in looking at deep learning methods for the recovery and also to relax the assumption of sparsity to more general models. Sorry, my voice is dying. Hopefully it will make it through the talk. But for the point of view of the talk today, this is more on the recovery side. The basic sensing ideas remain the same as we showed before. So putting these ideas together of the analog pre-processing and the digital recovery, whether it's using compressed sensing tools or more modern deep learning recovery tools, we could get all these different systems that are operating at very low rates. And again, those of you interested in more of the background, you could find them in some of our books on this topic. And these are heavily relying on this underlying notion of analog structure. Okay, so that's kind of some older principles. I do want to show some newer applications, and then we'll use that as a basis to move into some of the newer ideas of exploiting tasks and using deep learning as well. So one of the things we try hard in the group is to kind of try and defeat this quote by Albert Einstein, who says, in theory, theory and practice are the same. In practice, they are not. And, you know, that's of course true. But what we try to do in the group is develop theory, actually implement it. You know, it never works the first time, but by understanding why it's not working, go back to the theory and try to make the theory, you know, take into account more of the practical aspects and eventually get the systems to actually work. So hopefully I'll convince you that at least some of these ideas do really work in practice. And we'll start with ultrasound. Ultrasound is actually very, very similar to radar. So if there's people here that are more familiar with radar, everything I say for ultrasound is true for radar. It's just for me in particular, I like ultrasound because it has clinical applications, and we are working a lot with doctors to use these ideas in the clinic. So I'm excited about the clinical aspect of it, but mathematically, it's really the same as radar. So in the context of ultrasound, we've shown that by exploiting both the structure and the particular task of beamforming, we could reduce the rate quite substantially. So we sample at 4% of the Nyquist rate in every channel, and we dilute the number of channels by roughly a factor of square root. So, you know, instead of 100 channels, we have about 10 channels, each one at 4% of the Nyquist rate. So this reduces the rate quite substantially, and it allows some interesting things. So it paves the way to 3D imaging, which today is limited by the data. It allows for high frame rate, which is important, for example, in cardiac imaging. And the application that I'm most excited about is this wireless probe that we've been developing. So in standard ultrasound machines today, the probe is really just an analog device. So it transmits, it receives, it doesn't do any sampling at all because it's just too costly to do in the probe. So from the probe, you have this analog cable that goes into the machine, and only in the machine do you start doing the sampling and the processing and all of the post-processing as well. So now that we could sample at a low rate, we can actually do the sampling directly inside the probe. So first of all, we just get rid of the machine. There's no longer a machine, we just have a probe. What comes out of this probe are bits, of course, but these are bits representing not the image, but the actual, what we call channel data. So the actual reflections of the body. And this is important because the way the image is formed today by simple beamforming is, you know, the same method people have been using for 70 years. It's obviously not the best method. It's used for a computational reason. So once we have the channel data coming out of this probe, first of all, we don't need a machine. So we could just send it, you know, to an iPad, a cloud, a remote machine, whatever. Second of all, we now have the access to data that we can maybe process in more sophisticated ways. So let me show a short demo. Here, this cable is just for powering purposes, but the data is going straight from the probe to a local machine, to a remote machine, and to a tablet. And this is Dr. Shai Taiman Yilden, who we're collaborating with, and this is one of my former students. So this is a cardiac image, which is actually very hard because you have to do high frame rate.
Of the heart, we can see the mitral valve and the tricuspid valve. We can see the nice motion of the leaflets. We can see that actually there is good ventricular function and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject.
Okay, and now he's scanning directly to the iPad. So even though we reduce the rate, we're still getting very high quality images. Like I said, now that we have access to channel data, we can also look at doing things beyond standard beamforming. And one of the first things we did together with Professor Ruud van Loon in Eindhoven is we looked at whether we could do model-based beamforming. So in beamforming, you basically have weights that are predetermined, and we just learn the weights. We keep the overall structure, but we learn the weights from the training data is actually the image itself. So it's kind of like self-training. And you can see that, you know, we get much better performance just by working on the channel data itself and by adapting the weight. So it's still obviously very low cost, very simple to do. So the training is done on the actual image, on the actual channel data, and we get, of course, much better performance. So not only are we getting a simpler device, but it actually has better performance than the big machine because we have access to the channel data. So we've actually started a clinical forum in our lab where we have various different doctors that we're working with to try and see what else could we do with this channel data that we couldn't do before. Not just, of course, we're looking at it from a computational point of view, but we're very interested in understanding whether there's clinical value in this data that people didn't realize before. So for me, this is an exciting application because it's opening up, new clinical applications just by having a different acquisition strategy. So obviously, I'm not a doctor, and here we're relying on our clinical collaborators, but it's interesting to see how this interplay with technology can actually lead to new clinical input. Like I said, everything we're doing for ultrasound works equally well in radar. So I'll just quickly show, I won't go through this till the end, I'll show some of the demos we've developed in our lab in the context of radar, but they're very similar to ultrasound. So of course, in basic radar, the basic trade-offs are between bandwidth and resolution. Another basic trade-off is between dwell time, the amount of time you look at a target, and the Doppler resolution, and of course, the angular resolution and the number of antenna elements. So all of these trade-offs are trade-offs we'd like to try and overcome. And we could do that all by using this subsampling and compressed beamforming framework. So what you're seeing here is the system we've developed in the lab. That's the analog hardware. What it essentially does is just samples several bands of information instead of looking at the whole wideband. But then using these methods, it's able to still recover all of the information. So here you're going to see very high resolution range velocity. Even though we're sampling at a low rate, there's a lot of noise, a lot of clutter, and we could still get a very good delayed Doppler map. Now, since we only need some of the bands to do the communication, we can now coexist with communication channels. So basically, we could first locate the communication signals, and anywhere there's a vacancy, we can now send a radar pulse. And that's because we no longer need a very wide band radar pulse to get the desired resolution. We could do the same thing in terms of time on target. So instead of sending all the pulses in one direction, we send pulses in multiple directions, but still could recover each direction with very high resolution. So that's what we're showing in this part of the demo. And then the last part of the movie that I'll stop at some point is showing the same trade-off with spatial resolution. So we can dilute, that relates more to sparse arrays. We can dilute the number of elements and still get very good resolution. So one of the more recent applications we've been looking at a lot is automotive radar, where there are several of these elements are very important. So first, you want to do both radar and communication. So having joint platforms for that is very useful. You want to be able to see 360 degrees. So having ways to look at multiple directions at the same time is very useful. And of course, cost, right? You want to have multiple radars that are small and compact. So this is a demo we've developed for automotive radar, where we're combining part of these elements. So we're looking at multiple directions, and we can show that we could see all of those directions at high resolution. We're looking at joint radar communication. So we're interplaying the radar and communication in the same frequency regime. We could do this even if we don't know the pulse shape. So standard stream of pulses or FRI models, dating back to the work of Ederle and a lot of the beautiful, follow-ups on that, all assume that you know the pulse shape. Here we can show that we could combine this with basically blind deconvolution so that even if we don't know the pulse shape, we could still get all of the advantages I showed before. And we can show that mathematically, from a bound perspective, the price to pay for not knowing the pulse shape is a factor of 2. So we're still very much sub-Nyquist. We only pay a factor of 2 for not knowing the pulse shape. And we can show that this also works in practice. So it's not just a theoretical limit, but we could build a system that samples at twice the rate, or just take 2 systems, which is what we did over here. So we just doubled the number of receivers, and we could still get all of the advantages we've seen before with radar, even though we don't assume that we know the pulse shape. So all of these movies are on my webpage, and I know I'm skipping through them just to give you the high level idea, but if you want to see them in more detail, you could see them on our webpage. Okay, so like I said, we could, of course, apply all of these ideas spatially as well. And here we applied this to sparse antenna elements, so just using part of the antenna elements and still getting a very good direction of arrival recovery. Here, though, the way we choose the elements that we're going to use is not based on, more of the sparse array literature, but rather we use this model-based, I'll say more what I mean by model-based at the end, but we use this model-based deep learning idea. So we get better choices of antenna elements and could reduce further the number of antenna elements. And what you see over here is a demo where we actually build, these sparse antennas. And this is at Weizmann, where we're locating different targets. And what you see is that we could get almost the same resolution you would get with a full antenna array, even though we're using only a very small number of array elements. Okay, so that's basically what I wanted to say about structure and hopefully some newer applications of where this could be used. And now I want to move on. Actually, I'll stop for a second to see if there's questions and then move on to more about how we exploit the tasks. So any questions? Okay, so let me move on. So in what we've shown until now, we were basically exploiting the fact that there's structure either in the system or in the actual input. But often there's no structure, there's just some low-dimensional function that we're interested in. Like, for example, in ultrasound, these individual signals are very, very noisy, so they're not structured. But the beamform signal, like after we combine everything, is the structured signal. And it's also, of course, low-dimensional because there's one beamform signal, even though I started off with 128 input signals. So here we're looking at, even assuming there's no structure on the input, is the fact that I have a task. And going back to the question at the beginning, these are tasks that are relevant to the entire system. Like anytime you use ultrasound, you're going to do beamforming. So it's not a low-level task for a specific clinical application, but rather more a system-level task. So the types of tasks that we've been looking at, and I'll try to touch on them, depending on time, but we'll try to go through all of them, is, looking at statistics, looking at quantization, and we already talked about compressed beamforming, but I'll say a little bit more about that as well. So let's start with looking at power spectrum. This is actually a really interesting question that people have been looking at recently. And we know that there's many applications where we sample a signal, but all of the processing is done actually on the second order statistics. So let's say in array processing, DOA methods, AOA methods, et cetera, they're all done in the covariance function. In financial time series analysis, for example, also typically the processing is done on the covariance function. So this actually raises a very interesting mathematical question, which is if I have a random stationary signal, what is the minimal rate I need to sample it if what I want is not to estimate the signal, but to estimate its covariance? So let me start by giving some intuition as to why you would think that you could reduce the rate. So suppose we have a signal, let's just make this finite dimensional, although we really care about analog signals. And, let's say I have these 5 sampling points, and this is below the Nyquist rate. So I can't recover the signal. But now when I want to recover the second order statistics, I'm basically looking at time differences, right? Because I'm assuming, of course, the signal is stationary. So even though I have a small number of sampling points, what I need for estimating the covariance is actually the difference set, the set of all differences between these points. So even if the set is small, the difference set could be large. And of course, if I have n points here, I can have n squared points here, which means if you flip it around, I could reduce the rate by a factor of square root of n. And if you take that to infinity, you basically could reduce the rate down to 0. So we can actually prove this mathematically. So we can show that we could create sets that have a density of 0. So essentially the sampling rate is 0, but their difference set has a Berling density that grows to infinity, which means that I could use these sets to estimate the covariance. So I'm not going to go through the math of this. It's a little bit intricate, but the important thing is that when I want to estimate power spectrum, I could do that at much lower rates. So
Can I ask a quick question?
Yeah, sure.
Intuitively to me, though, it seems like the different set has a lot of redundancy. What's the intuition that I could say that it's like, it's only maybe constant redundancy or something. It doesn't boil back down to the original endpoints that you had.
Yeah, good. Another really great question. So you're right. I skipped that. The points have to be properly chosen. So not every set will work. The truth is random sets work with high probability. It's kind of like compressed sensing, right? So random sets work with high probability. Sparse rulers, essentially the sets that work for compressed sensing work here as well. But you could, and we do that in the paper. We actually go through like classes of sampling sets that are easy to do in hardware that would satisfy those conditions.
Okay.
But if I would take, let's say, a uniform set, then that obviously wouldn't work.
Right.
So you do have to be careful about choosing it, but we can show that there's general choices that are hardware friendly. Let's put it that way.
Great, thanks.
Okay, that's a very good point. So one of the earlier applications we looked at for this is in a cognitive radio system, where basically you just want to know, where the signal is, and you could determine that from the power spectrum. And here, this is the system we've developed for cognitive radio, where we sample at 6% of the Nyquist rate, and we could show that we get very good recovery, even if there's a lot of noise on the channel. So again, I won't play this to the end, but just to show the beginning. So at the top here, you're going to see signals that kind of change rapidly in time. This is their alias version because I'm sampling at a very low rate, but I could fully recover the power spectrum out of it. And if you see the video to the end, you'll see that we show this. There's a lot of noise under different considerations, and it still works very well in practice. Another cool application that I actually want to touch on, even though it has nothing to do with sampling, which is kind of why I like it, is to super resolution. Okay, so we use these ideas of covariance estimation in super resolution, and let me kind of try and explain that relationship. So we know that if we use, let's say, an optical microscope, which is very convenient, we're limited by diffraction. So we can't see details that are smaller than half the wavelength that we use for illumination. One way to get around that is, and actually won the Nobel Prize in 2014, is this really clever idea of fluorescence microscopy, where basically you input these fluorophores into the tissue and you control the fluorophores so that instead of taking one image, you now take thousands of exposures, where in each exposure, you make sure there's only 3 fluorophores that are fluorescing, and therefore you can basically just localize them. So every time you see a green spot, and the assumption is there's only one fluorophore there, you kind of stick a Gaussian there, and then when you sum over all of the exposures, you get one super resolved image. So this is the diffraction limited image. This is what you get when you have 20,000 exposures and you sum them up. So it's a really clever method. It won the Nobel Prize. So, that of course says it's clever. The Nobel Prize, interestingly, was in chemistry because the point here, of course, is not algorithmic. It's controlling these fluorophores. So that's kind of the clever point. But the advantage, of course, is that it gives very good spatial resolution. But the disadvantage is the temporal resolution. So you can't use this for live cell imaging because you have to assume that nothing moves, right, taking these 20,000 exposures. So basically, this is used on dead cells. You can't use this for live cell imaging. Now, if you think about it, this is actually a covariance estimation problem because these images are brightness images. So mathematically, it's enough to just estimate the variance in each pixel. And using the ideas we said before, we know that we could estimate the variance from a smaller number of frames. So what we did, and this method we called SPARCOM, super resolution correlation microscopy, because it's really based on correlation sampling, is that we took much fewer exposures. So here we have, on the order of 300 instead of 12,000 in the method behind the Nobel Prize. And we see that we even get better resolution. So we have better spatial resolution, but the important thing is that it's 2 orders of magnitude less data. Here we can see a cavity that you can't see in the storm data. Actually, the next step that we did is, again, combining this with model-based learning. So we increase even further the resolution. And the nice thing about doing it in a learning framework is that we don't have to know anything about the system. So here we assume that we know the system PSF. Once we did the model-based learning, and again, the learning is from a single image, so we don't need any training data. We don't even have to know the PSF either. And again, I'll say more about the model-based method towards the end. So the exciting thing for us about this is that now we could do live cell imaging, and we started a collaboration with a group of Professor Gilad Aran from the Weizmann Institute, where he's exploring the immune response of T cells by looking at T cell receptors. And until now, they haven't been able to view them live. So they had different assumptions about, what's happening under different conditions, but they weren't able to actually visualize that. And now using this method, we can actually visualize this in real time. So that's kind of cool. We're kind of excited about that. And the next thing that I'm also excited about, going back to the clinical domain, is that our next idea was to say, well, if we could do this for microscopy, maybe we could do this for ultrasound as well, because ultrasound is diffraction limited. I mean, the limit comes from the wave functions, just like in optics. So here, of course, we don't have fluorophores, but what we could do is we could inject these microbubbles. This is a bottle. It's an expensive bottle, but still, of microbubbles that you inject into the bloodstream. And we do the same thing as in optics. These bubbles kind of flow through the bloodstream, and basically we're tracking them just like we track the fluorophores, but we're doing this by tracking them in the covariance domain. And in the context of ultrasound, my student working on this called this method SUSHI, sparsity-based ultrasound, super resolution hemodynamic imaging. The point is we're trying to see small blood vessels, so that's the hemodynamic. And recently we actually did a clinical study with our collaborators, Dr. Ahuva Grubstein in Beilinson Hospital, where we wanted to use this method to see if we could give ultrasound super resolution capabilities in the context of breast cancer. So we scanned 21 patients with different lesions, where what you see here on the left are 3 examples. In all of these examples, obviously there's a lesion, but you can't see anything about that lesion. So there's no way to know if it's malignant or not just by looking at ultrasound. And that's why normally all of these patients would have biopsies. But after using this method, if you look here on the right, this is the output of our super resolution method. You actually see a very marked difference between these different lesions. And basically what you're seeing here is the vasculature. So you can now see the small blood vessels. And from a clinical perspective, the doctors were immediately able to determine that, this was malignant, this was a cyst, and this was a fibroadenoma, just by looking at the blood vessels within the tissue. So, I think that's a nice example of using a technique that's coming from sampling theory in something that has nothing to do with sampling, but hopefully could potentially be valuable. All right, so that's kind of some of the examples that we've been working on tasks. I want to move on now quickly to talk about quantization, but are there any questions? All right. So the interesting thing about sampling is that, we think of sampling as going to bits, but really sampling theory is typically not about bits. It's about going from continuous in time to discrete in time, but still continuous in amplitude. And then we have source coding, Shannon theory, rate distortion theory, et cetera, that looks at the quantization. But typically these are 2 different theories. What we looked at several years ago together with Andrea Goldsmith and her group was seeing that, could we unify the 2? So could we get a unified rate distortion theory that starts from an analog input, ends with an analog input, but tells us, what is the minimal distortion we could get for a given number of bits. So I won't go into that here. That's kind of heavy on the information theory, but the important thing is that we could develop these analog rate distortion curves. And then once we have them, we could ask ourselves, given that now we know what the minimal distortion is, could we achieve it by sampling below the Nyquist rate? Now, why would we think that we could sample below the Nyquist rate? I'm not assuming any structure here. The point here is that quantization introduces distortion. So when we say we're sampling at the Nyquist rate, that's the minimal rate to perfectly recover the input. But once we quantize, we can never perfectly recover the input anyway. So, maybe it's an overkill to sample at the Nyquist rate. Maybe we can introduce distortion that is not going to further increase the distortion from quantization. And it turns out that that is indeed the case. So what we're plotting here from the general theorems we developed is the minimal sampling rate you need to achieve the minimal distortion as a function of the number of bits. Now, of course, when the number of bits goes to infinity, you're back to the Nyquist theorem. So this black line is the Nyquist rate for these 2 inputs. So these are 2 different inputs that have the same bandwidth. And you see that for lower bit rates, we could sample well below the Nyquist rate and we're not losing anything. And this is just because we're quantizing. Now, what's also interesting is that you can now look at inputs that are not band limited, like this Gauss-Markov input, and still get a finite optimal rate. So we could get finite sampling rates even for non-band limited inputs that are optimal. You can't do better than that just because you're quantizing anyway. Okay, so these are theoretical results, just like any rate distortion theorem. And the next thing we wanted to look at is whether we could achieve these results in practice using simple hardware. Now, of course, in general, the answer would be no, right? So if we use simple scalar quantizers, we can't achieve rate distortion curves. But what we wanted to do, kind of in the spirit of compressed sensing, but there's no sparsity here or anything like that, is to say, okay, let's look at systems that we're constraining in advance to have this form. We're going to go through an analog combiner. So we're going to do analog mixing. We're then going to have simple scalar quantizers and, of course, post-processing. And we're going to do joint design of this system. So we're going to jointly design the combiner, the post-processing, and the scalar quantization. And we're going to do that in light of a task, where again, a task is something general. So let's say this is a communication channel and we want to estimate the channel or localize the source or recover the underlying bits. And what we can show is that using this really simple hardware that we actually built in the lab because it's simple, we could achieve these optimal rate distortion curves, even though we're doing scalar quantization. So by allowing to do this combining and taking the task into account, we can both sample below the Nyquist rate in the analog domain and quantize with a very small number of bits using a very simple scalar quantizer and still not lose anything. We're still achieving these optimal analog rate distortion curves. So we've looked at this a lot in the context of MIMO channels. There's been a lot of work in MIMO of using low bits because there's many channels. And the nice thing is that we can show that by using this method, just kind of introducing that analog combining, we can actually get much better performance than all of the existing techniques. And let me just quickly show very briefly, again, a demo that we've developed in the lab here. So what we're doing is we have a MIMO channel with multiple RF chains. We're sampling only a small number of the chains, and each chain we're sampling with, I think here it was 2 bits of information, and we could still perfectly recover the underlying channel. Just 2 last points before we end with the model-based deep learning. So before I showed how we do that with RF hardware, so we can use RF hardware to do the combining. More recently, we've been looking at metasurface antennas, dynamic metasurface antennas to do the combining. So these are basically elements that you could change their response by changing just the current through them. So these metamaterial elements have different responses dependent on the current. And this is work that we've been doing together with a group of David Smith, who's an expert in these metamaterials. And the nice thing about using the metamaterials is that they're very cheap, they're very low power, and you can actually get very elaborate responses that are even frequency selective by just changing the current. So they're very simple to operate, and therefore we could get like very efficient analog precoding. The last thing I want to say before we end kind of with the model-based deep learning is that we've spoken a lot about kind of communication separately, radar or ultrasound separately, and more recently there's been a lot of interest in how to combine them. So how to do dual function radar communication. Maybe, in the interest of time, I'm not going to go into too much detail. We have a recent review that we wrote on this topic for whoever's interested, but basically, the 4 basic ideas, which you could kind of guess, are either just designing separate signals that are coordinated, embedding radar in comm, designing one signal that's optimal for both, or embedding common radar. So you could take the ideas we've spoken about before and kind of apply them to these different systems. Let me just briefly show an application where we embedded common radar, but again, you could do it in other ways as well. And here, basically what we did is we embedded the communication in the frequency selection and the antenna selection. And because we know that we could get good recovery even without using all of the antennas or without using all of the frequencies, we could very efficiently embed communication symbols that way. So let me just skip right away to the demo. So this is a system we've developed in the lab that's doing this joint radar communication. And basically it's taking the same ideas we talked about before, but using them to encode communication bits in a radar system. And this allows us to get almost perfect both radar and comm performance, but we're doing them at the same time, in the same frequency, on the same platform. All right, so let me approach the end. I think, how much time do we have left?
Well, there's 10 minutes, but also we want to leave time for Nicole. She's going to do the short discussion of your talk, and hopefully, and get people engaged with questions and stuff. So if there's a few minutes left for her, that would be great.
Okay, perfect. So let me try to do this in 5 minutes. I guess to everybody's advantage, I'm hoarse, so I'm probably talking slower than usual, but All right. So, okay, let me just say 2 words about model-based deep learning. I've mentioned it in different parts of the talk, but everyone knows that deep learning, is everywhere. But if we look a little bit closer, when we say is everywhere, it's particularly successful in problems that have been traditionally difficult to attack with conventional methods. So, we could spawn faces if you really want to do that. We could get, very good classification, detection, et cetera, et cetera. But we know that this needs, very large training sets. The methods are not interpretable. So often, you kind of feel like you just put everything in the pile, stir it. If it doesn't work, you stir it again. Eventually it's going to work. It's computationally very exhaustive to train. We have an enormous amount of parameters. It's not clear how well it generalizes, et cetera, et cetera. So, the success, of course, comes with a high price tag. If we look at kind of signal processing, which we all know and love, then signal processing is heavily based on models. The advantage is that it's easy to incorporate domain knowledge and structure. We could get inference from relatively small amounts of data. We have very nice analytical techniques to assess our output. But of course, this has disadvantages as well. It requires knowing the model. Okay, so that's probably the biggest disadvantage. And of course, the inference could be slow. So even if we know everything, the problem could still be mathematically quite complicated. So what we've been looking at a lot in recent years is how could we combine the two? So let me kind of very briefly, I'll skip some of the animations here, try and illustrate 2 of the approaches that we use to what we call model-based deep learning. So one is based on optimization and the really nice idea of unfolding. So actually, I'll skip ahead. So one is using the ideas of unfolding, and the other is using this notion of a hybrid plug-in method. So unfolding dates back about a decade ago to a really, really nice paper of Gregler and LeCun that looked at unfolding in the context of sparse recovery. But in recent years, there's been a lot of interest in this, and we've been working on it quite a bit. So those of you interested, we had a recent review in Signal Processing Magazine that you could read more about this. So essentially what you do in unfolding is you start with your kind of favorite iterative method to solve your problem, where the problem, of course, is defined by some underlying model. You then unfold it. So you write down explicitly, let's say, T iterations of your method. So up into here, you're just solving an iterative algorithm. But then the last thing you do is kind of free some of those parameters. So each layer here is going to depend on parameters of the problem that you now don't want to assume that they're known. So you free them and learn them from data. So for example, if we go back to, let's say, the super resolution method, we showed we free the parameters of the PSF and we learn them from data. So we basically end up with something that still looks like an iterative algorithm, still coming from an underlying model, but whatever we don't know, we learn from data. So we've used this in many, many applications. Just to quickly show a few. So we've worked with Michel Mongan using this for deep blurring, and basically we just unfold a total variation problem in the gradient domain, and this leads to a network that has 10 layers, so very simple, but it appears to do better than state-of-the-art methods in deep learning, which are much more complicated. We've used this, like I said, for super resolution in both ultrasound and microscopy. And here it works really, really well without even needing any training data. We've used this for signal separation. So we've looked at problems. This is ultrasound. The same thing happens in radar where you have heavy clutter. So in this case, this is the blood flow, which is sparse, but you have heavy clutter from the tissue. And we modeled that as low rank and sparse, but then unfolded it into what we call, well, actually, we called it Corona 2 years ago. So that was before COVID. So it kind of became viral, but this was really before. We did not predict COVID. But anyway, it stood for Convolutional Robust Principal Component Analysis. So I'll skip the details of that. So that's kind of one method you could use. And we've been looking at using it in many, many applications. More recently, we've been looking at trying to get theoretical proofs to the fact that, as we see, it works very well in practice. The other method we've looked at is actually starting from the algorithm itself. So in unfolding, you start from the underlying optimization, but there's many problems, and communication is a good example for that. Like, let's say the Viterbi algorithm, where you have an existing algorithm. It's not really a solution to an underlying optimization framework. It's kind of a very good heuristic, but that heuristic depends on things that you don't know. So what people are doing, like in any other field, they're kind of replacing that with a large deep network that learns end to end. What we're saying instead is you could go back to that method, kind of write it down in blocks, and take only the block that depends on something you don't know and replace that with a network that's only learning it's input and output, not end to end. So this sounds very simple. It actually is very simple, but it works very well in practice. So for example, we've used this for what we call the Viterbi-net, where we develop a deep learning based Viterbi algorithm, but instead of replacing symbol detection by end-to-end learning, we keep the Viterbi structure, we keep the whole dynamic programming, and we only learn the likelihood, which is very easy to do. And not surprisingly, this works actually much better than end-to-end learning methods that are much more elaborate. So in the interest of time, I'll just skip to the end. So we've used this for many problems in communication, for factograph methods, for successive interference cancellation. Last thing we've used it for is COVID. Actually, we've looked at these methods for COVID detection, both from X-ray images and from ultrasound images. And just by using this model-based approach, we've been able to get really, really good performance on very diverse data sets. So let me really wrap up. We've tried to get across how we can exploit structure and goal and tasks in both model-based methods and data-driven methods. We've spoken a little bit about new mathematical limits that you could get from this, new engineering principles or technologies that you could get from this. And at least for me, the most exciting thing that we're trying to work on more is how we can use these ideas to get different scientific insights and clinical insights, because now we could see things that we couldn't see before. So I've skipped through the technical details. Those of you interested can find more on our webpage and on our books on the topic. Of course, none of this would have been possible without my amazing group of students. So of course, COVID picture, but they all do actually have faces. And of course, my amazing, amazing collaborators that I've had the honor and pleasure to work with. And thank you very much for your attention.
Wonderful. Thank you so much for the very interesting talk and all those like amazing applications. So that's great. Okay, so now we're going to go to Professor Nicole Sieberlich. I hope I've pronounced that correctly. And Nicole is going to present this short discussion of her perspective from the papers that you shared with us, Yonina, and including to sort of generate some discussion among the attendees.
That's great. Thank you so much for doing that.
So, hi, I'm Nicole Sieberlich. I'm an associate professor in the Department of Radiology here, and my research focus is rapid and quantitative MRI with an emphasis on targeted acquisition and reconstruction. And Dr. Eldar has also done a lot of work in that area, so I'm going to try to pose my question in that direction. But before I do, I just want to say this was really a fabulous talk. There's packed full of so many things. We needed 3 hours, I think, to go through it, so we'll have to have you back again. Okay, so I was really interested in the model-based deep learning for quantification, specifically using the magnetic resonance fingerprinting algorithm, which a lot of us on the call are familiar with. And again, you've done a lot of work in that area, and so I kind of wanted to pick your brain on some issues that may arise that I think maybe the model-based deep learning could help us with. So I unashamedly stole this picture from one of Dr. Eldar's papers on the work that she's done in fingerprinting, just to explain how this works. So basically what we're doing is collecting some sparse MRI measurements, which we then convert into a time series of MRI images. And then we try to use this time series of images in order to estimate some physical properties of the tissues in a pixel-wise manner. And so the way this is usually done is we model so we modeled the actual acquisition as being a function, or the data we collect is a function of these tissue properties, which is then subsampled. And so our job is then to go from these measurements back to the tissue properties. So conventionally, what we would do is make this giant dictionary of a link between all of these signals to all of these tissue properties, and then just do, like, this is simple model-based reconstruction, just do a fit. But this is really slow. We have errors because our dictionary is quantized. We can't, do every single combination of all these parameters to figure out what the signals would be. And we need a huge amount of storage because these dictionaries become really large in some cases. And so what Dr. Eldar has done is to build a deep convolutional neural network, which takes this task from a purely model-based reconstruction where we're trying to assign each of these curves to a set of tissue properties, and makes it into this beautiful neural network. This is much faster. We don't have dictionary quantization errors. We don't have to store a lot of parameters. And this is worked really well. I'm not going to go into this too much because we're running out of time, but compared to the reference, if we look at the standard matching, which is what I would use, we have some errors, but if we use the deep learning approach, then this is looking a lot nicer in T1 and in T2. But our issue comes in what model we choose to use. So we use the block equations. I apologize, it's kind of crossed off here. So what this does is it allows us to model the link between the tissue properties and the signals that we actually get. And those are pretty well defined. We can write that down, but they're not always completely accurate. And so when we use them for our parameter restoration on the opposite side, we may have some mistakes. So what's going on here, right? The problem is because we're physicists, we like to look at, if we look at 1 pixel of tissue, we imagine it's this giant chunk of homogeneous tissue, right? It's easy to model. It has one set of tissue properties that are associated with it, but this is totally not the case. If we're talking about real tissue, it has blood vessels and cells, and each of these, the extracellular matrix and the cells and everything, they have their own tissue properties, which we're not modeling at all with a basic block equation simulation. Sometimes we can just model tissue as a big block, but there are lots of other tissue properties that we might have to take into account, which we also typically don't want to because it's just a lot of parameters in our model, which gets a little messy. And maybe we can get to a simpler model if we collect our data properly, maybe even losing some other parameters. But we don't really know necessarily the space that we're in because we'd have to simulate it, and we don't really want to do that for all of these different possibilities. Okay, so we want to model it as simple, but we know it's not. And so I was struck by this statement in one of Dr. Eldar's papers that model-based algorithms are typically sensitive to an accurate knowledge of the underlying model as parameters. This is exactly the problem that we have. But we may be able to use like a model-based deep learning algorithm in order to kind of guess in some of those areas where we don't really know what the values are. And this is what exactly we're getting at the very end. So my question, I have 2 questions, but I'm just going to stop with this one, is might it be possible to construct a model-based deep learning framework that will tell us if our model is appropriate, and if it's not, help us adjust? So we don't want to assume that we're wrong always, but this is kind of going beyond just saying help us figure out where we're wrong, but it's like maybe we're wrong and maybe we're not, but how could we give ourselves the flexibility to do both of these things at the same time? That's
Thank you so much for that discussion. Yeah, Yonina, go ahead.
Oh, I wasn't sure if it was for me or for the audience, so.
I'll start with you.
Okay, cool. Well, first of all, thank you so much. I'm like humbled by somebody presenting my paper. So yeah, that was a great, you do a better job than I do. So that was great. And I think, as you know, we've spoken about it. I think MRI is a really good area for these kind of things. So I'm happy you're raising it. So one of the, let me try to, to answer here. And I think this is a really good point. So let me go back to the PSF problem, because I think it's very similar to here, where here the dictionary is playing the role of the PSF. So if you think of a model-based network in the context of PSF, and then I'll translate it here to the dictionary. So let's just look at a very simple model, right? Like, let's say I have point sources, they go through a PSF, and I'm trying to recover the point sources. So, that's presumably like a really simple deconvolution problem. But if there's a lot of noise, or if the PSF is not really a PSF, right? Like, by saying a PSF, you're assuming that things are spatially invariant and it doesn't depend on depth or anything else. So what if that's not the case, right? Which I think is similar to what you're saying here. So like in ultrasound, we know that the PSF at the end depends on depth. It's not spatially invariant, etc. So if you do like this model-based framework, you could think of it as like you're solving a gradient descent, but in each layer, instead of having the same PSF, you're actually allowing for a different PSF, because you're allowing each layer to learn a little bit differently. Now, when you concatenate PSFs through a nonlinear, because there's a nonlinearity there as well. So when you're concatenating these PSFs through the nonlinearity, it's not the same at the end as having one underlying PSF. So this we've actually studied quite a bit, and it's interesting because if you just look at a small number of layers, like 3 or 4, it's not the same as saying I have an unknown PSF and my network is learning the PSF. It's not. It's the network is building some hierarchical version that's not spatially invariant. It's not depth invariant. It's taking a simple PSF and kind of breaking it up to a nonlinear concatenation of these underlying PSFs. So I think this really captures what you're saying here. Like, I model it as having a dictionary. Now, if I look at one layer, then I will be just learning that dictionary. But if I allow it now to add layers gradually, like instead of just fixing layers in advance, I gradually add them, then it's like I'm allowing it to correct itself if the previous layer wasn't enough. And by each layer that we're adding, we're not better learning the PSF, we're actually adding complexity to the assumption that there is a single PSF.
So I am exactly the opposite person who should be asking this question because I know very little about deep learning. But so is the idea though that you would train it with one layer and then say, okay, well, that wasn't quite enough, so we're going to train it now. We have the first layer trained and you add a layer, you really just train it layer at a time?
Yeah, so that's a really good point. That's a really good point because I was just talking conceptually. So the standard thing people do today is they actually fix the number of layers in advance. So they say, okay, we're just going to assume 10 layers and now I learn it end to end. For what you're describing, I think that would not be a good approach. It would be better to say, let me do this gradually, because like you're saying, if a simple thing works, I want that simple thing. And we have been looking recently, although again, not in a principled fashion, but I have a student looking into this of doing what you're saying, like saying, okay, I want the learning to be greedy in some sense. So I'm going to learn one layer and then I don't want to retrain. I'm going to keep that layer, add a layer, but in some smart way by correcting, doing a slight correction and moving on in a greedy fashion. So I think, this is work in progress, but I think it would fit very well what you're describing as well.
That is really interesting.
Yeah, so now we have what to write in our proposal.
Now we know exactly. I was partly using it for that too.
Another thing, by the way, I know you didn't ask it, but let me just say it, just to put it out there. Another thing we didn't do in our paper, because that was still from like, I don't know, a year or two ago, but I think we should, is that there's two parts there that are not heavily correlated. So there's the part that kind of learns the dictionary. There's the part that learns the structure. They're not well combined right now. There are two blocks that are kind of side by side, but really in this more model-based framework, you should cycle through the whole thing and that should be one layer rather than, doing one, doing the other and putting them together. So that's another thing I would improve.
I completely agree. Awesome.
Great. Are there other questions from the audience? Thank you again, Nicole, for that really interesting perspective.
Yeah, totally.
I can ask a quick question. Thanks for the talk. So I have maybe a little bit of a technical question about the part where you argued maybe we should learn, if we have a pipeline of model-based approaches, maybe we should learn something in the middle of the pipeline if we are putting lots of unknowns in that thing in building our models. In a sense, but we don't have data for the input output of that part other than the data coming from our own model there, which we don't want to fit the neural network to. So do you need to somehow able to back propagate from what's downstream in your algorithm so that you can train and figure out how to learn that specific part?
Yeah, that's a really, really great question. So the answer is really, it depends, right? It depends on the setting. So specifically in the Viterbi context, that block is just a likelihood block. And I could easily train it independently of everything else because I could just generate, I don't even need real data in a sense, right? I could just generate it, I could simulate it very easily and just learn how to perform likelihood computations without having to do the end-to-end network. So kind of, again, and that's kind of, lucky, so to speak, but we found that in other applications as well, that the actual block that depends on something you don't know is actually a block that's quite easy to learn independent of the rest of the system. So in communication, in most of the applications we looked at in communication, that was actually the case. Because usually the difficult computations are likelihood or map or, those type of computations, which you could actually even just simulate in MATLAB. I don't even necessarily have to have real data. But that's not always the case. So they're we're lucky in a sense. But of course, there's problems like you're saying where I don't have input output, or I can't easily simulate input output for just the individual block. So then what we would do is like basically what you said, right? I would use the total input output data, but but I learn only that small block. So everything else is fixed. So when I back propagate, I'm only back propagating through that block. I'm not back propagating through the entire system. So the input output is through the entire system, but the back propagation is only through that block. Everything else is fixed.
Thank you.
Sorry.
Other questions? All right, VJ, you wanna?
Well, I was just going to say that since there are Yonina has some meetings scheduled, what I'll just do is let's have it on the same Zoom. I'll turn off the recording and then you can just proceed on that, if that works
Okay,
out
sure.
fine. Because everyone's
I
on.
Then I can ask my question since I'm in the first meeting, so.
Yeah.
Oh. Good. I was just
Okay.
wondering where I'm supposed to move. So that saves.
Well, I'll just terminate the recording and then we're all set. Yeah.
Thank you so much, Professor Eldar, for the